So if you listen to the tech hype right now, the future of AI is already here. Fully autonomous AI agents that can run entire companies, write complex software, and solve your biggest business problems with just a single prompt. But if you've actually tried to build one of these systems for a production environment, then you know the truth. I'm Derick Chen, and this is BuildWithDC. As a senior AI development engineer at Google, I build these exact types of autonomous systems with large, complex organizations. Evolving AI complexity is my daily mission. And before this, I spent my time at AWS driving enterprise AI development adoption across 7 APJ countries to achieve 10x impact. The reality is that creating an autonomous AI system is about 50% AI and 50% harness. It's not just about a model. It's about the orchestration, the memory loops, the guardrails, and the deterministic code holding it all together. We're currently living through a massive paradigm shift. Right? We're moving away from deep, single-function generative AI applications, like a single chatbot or a basic summarizer, and moving towards a broad, goal-oriented, agentic mindset, spanning across multiple applications and business domains. But as an engineer, every single time you move the needle towards autonomy and higher complexity, you aren't getting it for free. This is nothing different from building software 2.0 that we have so much experience of. Evolving your AI architecture is a constant negotiation of trade-offs. You are trading deterministic predictability for flexibility, or trading low latency for reasoning. And of course, you're trading your cloud budget for token consumption. So in this video, we're going to look past all that marketing stuff. We're going to look at the actual engineering maturity model of AI systems, from just the basic workflows to multi-agent swarms, and look at the exact same technical triggers that can tell you when complexity is worth the cost and when it's going to break your system. So let's dive into the architecture. To understand where we're going, we first have to look at how we got here. The evolution of generative AI architecture is actually a very logical progression. It starts at the baseline, right? You have a simple LLM prompt to ask a question and the model generates an answer based on purely its training data. And knowledge was just an API call away. Next, engineers realized that model hallucinates without facts, so we added retrieval RAG or retrieval augmented generation. We built a database onto the LLM to give you more context. And then we wanted the model to do actual things, so we gave it actions via tools. Now the LLM can trigger an API call to send an email, to update a calendar, or to create a live system. But the real bridge to agentic system happens when we introduce the reasoning loop. This is when the model doesn't just execute a tool, it evaluates the output of that tool, thinks about it, and then decides what to do next. This brings us to the level of agentic maturity. Right? Level 1 is basic. Think of this as basic workflows executing very specific linear tasks. And level 2 introduces dynamic behaviors. The agent is given a pre-approved set of tools and gets to choose which one to use based on the user's prompts. Level 3 is where it gets a little bit more interesting. The reflective agent. Here, we introduce the react pattern, reasoning and acting. The agent can self-correct, identify when a tool fails, or try a different approach without human intervention. This is the foundation of a true autonomy. But just because you build a reflective agent doesn't mean that you should. This brings us to the core engineering dilemma: workflows versus agents. Let's be clear about the difference. Deterministic workflows use predefined logic and code paths. As a developer, you set the exact sequence of events. You know exactly what path the data will take. Whereas for autonomous agents, on the other hand, they dynamically direct their own processes. They use a feedback loop to constantly assess their progress towards a goal, deciding on the fly what next steps to take. This leads us to the golden rule of AI engineering. It's the same as before, right? Keep it simple. A well-designed single agent with the right set of tools, wrapped in a deterministic workflow, will often completely outperform a complex multi-agent system. Why? Because you have to strip away the massive token overhead, the latency of models talking to other models, and the compounding risk of logic loops. Don't build an agent if a script will do. So what happens when your system actually needs to do more? Extending an AI's capabilities ultimately comes down to solving two problems, right? Managing context and deciding how to delegate tasks. You basically have two choices. You can either go for the integrated agent skills or delegated sub-agents. Let's look at the integrated skills first. If you tried Claude Code or any of the agentic coding tools, you shouldn't be a stranger to this. This means loading detailed instructions directly into your main agent's context window. The massive pro here is token efficiency through progressive disclosure. The agent pulls only what it needs, when it needs it, and you get a full transparent visibility into its internal reasoning path. And the alternative is delegated sub-agents. Instead of loading up the main agent, you spin up independent specialist agents in complete separate sessions. The trade-offs here are steep. You instantly inherit higher token costs due to the overhead of those agents coordinating with each other. Plus, the internal thinking of sub-agents is entirely hidden from the main process until the task is completely finished. It's a black box inside a black box. Debugging can be painful without mature observability. So with these costs in mind, when is the complexity of multi-agent system actually worth it? You shouldn't cross this chasm unless you hit specific technical triggers. Trigger number one is context protection. If you have a high token volume subtask, like reading and summarizing a massive document that costs thousands of tokens, you need to isolate that. So you spin up an isolated sub-agent to protect the main agent's reasoning and context. Trigger number two is parallelization. If a user query can be decomposed into multiple independent research tasks, then spinning up concurrent sub-agents in the fan-out pattern can dramatically reduce the latency. You are trading token cost for speed and thoroughness. And trigger number three is specialization. When your primary agent is overloaded with more than 20 tools, its performance will start to degrade. Or if a single agent is forced to judge conflicting personas, like being a strict security code reviewer and a creative brainstormer at the same time. This is the time to split the work based on the functional outcome goals. But remember the hidden costs. Multi-agent coordination typically uses more than 3 times the token of a single agent. You risk critical context loss during the handoffs between agents, and your maintenance overhead skyrockets. Work should only be split when the context can be truly isolated. If you master all these trade-offs, then you reach the ultimate endgame, swarms and ecosystems. This is the top of the maturity model. And to be honest, very few teams can build and operate such systems well today. So level 4 is your standard multi-agent system collaboration, where distinct agents pass messages to achieve a common goal. And level 5 is the managed multi-agent system. Here, you introduce a meta agent or an orchestrator that oversees its sub-agents, dynamically assigning tasks, monitoring performance, and enforces system policies. And level 6 is the frontier, self-improving ecosystems. This is where the actual swarm intelligence takes over, utilizing iterative feedback loops across hundreds of specialized agents to discover novel solutions that no human explicitly programmed them to find. But here is the final reality check. Building at this level requires immense architectural discipline, strict fault tolerance, and rigorous compliance checks. Because at the end of the day, no matter how autonomous the system feels, it is still software, and it's non-deterministic. So always start your architecture with a single agent baseline. Only add complexity when the engineering trade-offs mathematically make sense for a specific business problem. Don't chase the AI hype, don't build agents just for the sake of it. If this breakdown helped you rethink your AI architecture, remember to hit the like button. Subscribe for more deep dives into software engineering. And let me know in the comments what kind of systems you are building right now. Thanks for watching. My name is Derick Chen, and this is BuildWithDC.